Well, good afternoon and welcome to the last presentation of this afternoon before the banquet. As you can see, the title of my presentation is sort of limited, but I will actually go beyond that because radiation protection superstitions threaten not just geologic isolation of radioactive waste, which is my area of expertise, but they threaten a lot more, and they threaten every one of us. So I'm going to start with a few fundamentals, and then I'll go more into the area of geologic isolation of radioactive waste. My expertise is actually started with geology. I have a degree in geology, master's degree, and to just illustrate my expertise in the field of waste repositories, specifically geologic repositories, I edited a book edited by the printed by the Geological Society of America on geologic repositories. If you're interested in that one, it's out there on the table. There is a copy for review, and there are instructions as to how you can order it. It starts with a chapter on natural nuclear reactors, which I may have the time to talk a little bit more about at the end of my presentation. And it ends with a paper by Bernie Cohen, whom some of you still remember, on the potential actually of any place on the planet 500 meters deep or deeper below the surface to isolate very effectively any kind of dangerous waste. So if you just throw a dart at the map and just go 500 meters deep, you have a good geologic repository. You don't really need a lot of money to spend on site investigations, and he makes a very persuasive argument for that. The big thing that we always have to keep in mind when we're dealing with anything nuclear or radioactive is that there are a lot of sacred cows out there that require to be slaughtered, that deserve to be slaughtered. And the chief among them is that ionizing radiation in any intensity, in any amount, in any quantity is mostly unnatural, unusual, always dangerous. So let's see if we can help slaughter this sacred cow. Of course, we start from a point of great disadvantage, and that is when normal Americans and regular people all around the world hear the word radioactive, they go like this: keep me from this, I don't want anything to do with it. And these newspaper articles actually, or the headings of these articles, illustrate the point. You know, if in the political realm, if the left wants to say anything about a right-thinking person, then they call his opinions or her opinions radioactive, whether it's Glenn Beck or Ann Coulter or anyone like that. And we cannot be sure that we even get good information on radioactivity from very established, very respected scientists. I don't really like to disagree with Stephen Hawking, but I would recommend that you take that statement that's mentioned in this slide with a small grain of salt, because it's too general. And the next slide actually tells you why. There's very little information out there on what in actual numerical values is the exposure to astronauts that go out into space. But the general statement is always that, oh my God, there's that cosmic radiation, and astronauts are being threatened on long-term missions into interplanetary space by this radiation. This is actually a illustration published in National Geographic a few years back. And on the right-hand side, you see the exposure for a Mars mission of roughly 3 years. And we heard that earlier discussed slightly. We have had in the past as a speaker here Robert Zubrin, who wrote a book about the mission to Mars. And I asked him at a previous DDP meeting whether he actually agreed that this issue of exposure, of radiation exposure to astronauts going to Mars was actually overblown, and he said yes, it is. It's probably not going to be a significant issue. Because One of the things that we need to always keep in mind that everything around us is radioactive. This planet is radioactive. The universe is radioactive. If we don't like radioactivity or nuclear processes, we are living in the wrong universe. And furthermore, we need to remember something that Gerald Looney said, and many of you remember Gerald Looney. He was a former president of this organization. And I have never found this principle expressed better than in this slide. You know that when we were children, our mother told us, before we cross a street, always look left and look right. And most scientists dealing with radioactive and nuclear issues, and most scientists actually don't know anything about nuclear or radioactive issues, they are violating that principle every time, because they are looking only at the potential negative consequences of radioactivity. And one of the things that happens is that, for example, in my own profession, geology, most geologists know about radioactivity because of the principle of radioactive decay and radiometric dating. We know that something radioactive today becomes less radioactive in the future. But what most people never think about it, if it becomes less radioactive in the future, then it must have been more radioactive in the past. So the planet was much more radioactive in the past, and life actually started under conditions of higher background radiation than we have today. So that this idea that every little increment of radiation, in addition to what we have in nature, is somehow dangerous to organisms, just does not compute from a geological and biological and evolutionary perspective. It just does not really make any sense. And here's a chart that I put together based on information from this report written by a Russian in the 1960s. The Israelis translated it. And it's today available on the internet as actually a report by the International Atomic Energy Agency. I suspect that very few people ever read that report. But it makes the point that planet Earth was much more radioactive in the past than it is today. So what we have here on the bottom is, if we set arbitrarily today, at the present, the values for the main isotopes that we have occurring on nature in the Earth's crust, U-238, 235, thorium, and potassium-40, arbitrarily set them at 1, and then we go back 2,000 million years or 2 billion years ago and 5 billion years ago. This is what the concentrations were, or what the percentages were in radioactivity in the past. We can see that the planet was much more radioactive in the past than it is today. And if we have the time at the end, I'll talk about natural reactors. We not only know that radiation, background radiation specifically, varied throughout history. It was more in the past than it is today. But we also know that it varies planet-wide by significant amounts, by up to 2 orders of magnitude. And the highest known background, radioactive background today in the whole world, there may be others, but we haven't found them yet, is a little place called Ramsar, this town right there in Iran, right on the shore of the Caspian Sea. And you can see some values here for Ramsar compared to what's considered normal or average on the planet's surface. Radium, radon, and then the population dose. That's sort of the number that we'll come back to. So the population dose that we have here in the United States is the natural population dose. It's on the order of 3.6 millisieverts per year. Okay? Over in Ramsar, it's up to 250. So if we take the 2 and the 250, that's 2 orders of magnitude, or a factor of 200. Now, the important thing to keep in mind is that this has been researched by several eminent scientists. They have found absolutely no evidence that the people that are living in Ramsar and are exposed to these high doses live shorter lives, have more cancer, or otherwise are exposed to any kind of detrimental consequences of living in this high background environment. That's what we need to keep in mind, and that's actually where we should set our radiation protection regulations. As we'll see here in a little bit, we are far from that ideal. This is actually what radiation regulations look like compared to the natural backgrounds that we have in various areas of the world. The scale down here goes from 0 to 2 rem, and up here it goes from 0 to 100 rem. So this one here is an expansion of this very short interval up here. And you notice where we regulate. We regulate down here, EPA and NRC numbers. Then we see, this is Santa Fe, New Mexico. That is actually a granite statue in that park, and if you're sitting on a park bench right next to it, that's the exposure that you get from the granite, which is fairly radioactive as rocks are concerned. Then you see the current occupational dose, maximally exposed individual, okay, 5 rem per year. Then you see the standards as they were set in the 1930s. Ramsar here, the town in Iran we just saw earlier, is given as 79. That's a dose that's in a particular spot. Actually, this is a good example of how you have to carefully read some of those reports, because that 79 rem per year is not the dose that an average person would get in Iran. They would get about 25 rather than 79. The 79 are some spots on the wall. If somebody would spend his entire life basically standing in that one spot, that's what he would get. But nobody stays in one spot the whole year. So the more realistic value is roughly 25 here. But you can clearly see we are regulating way below the natural variability of background. And this was published in 2003 in the Journal of the American Nuclear Society. So, you know, it's not data by some kook that published in an obscure journal. So anytime we talk about something nuclear or radioactive, our BS detector has to be actually on high alert. And this is no joke. This is actually an academic treatise, as you can see, Princeton University Press, and I like to quote that every time I get a chance. So I am not the one who invented or who found or discovered most of the information that I'm passing on to you here. Actually, I found hardly any of it. I'm standing on the shoulders of giants. And all of these gentlemen over here that you see in this picture, I call them in analogy to the Ghostbusters, the RADCON busters. RADCON stands for radiation control, but the con can also be taken as meaning something different, and that's what I usually like to think about. And every one of these gentlemen, save one, has actually, I believe, talked to this organization. Bernie Cohen, who is now passed away, Myron Polikov as well, Bobby Scott is still around, and of course you see Edward Calabrese right here. I'm really glad to include him in the picture. Jim Mucker had died, I believe, last year, and this one here is a German scientist who has written quite a bit about radiation standards and radiation protection standards and the irrationality of what we're doing today. So I'm standing on the shoulders of all of these giants and several others that didn't fit into the picture. A few years ago, I came up with this slide, and which is stolen from a lot of people. You see Ted Rockwell, who actually talked also to this organization, and then Zbigniew Jaworowski, who was an eminent Polish researcher in this field. What you see here is, again, a scale, and you have it here in both the SI units and the sort of conventional units we use in the US. The scale on the right hand in rem, and on the left in millisievert, and you see the equivalence right there. So 44 rem is 40 millisievert, for example. That lower part of the scale is expanded here on the left. So this one here goes from 0 to 1. You see 0 to 1 here is just a very small scale. So everything that we usually, or that the press reports as threatening to us or potentially dangerous to us, like Chernobyl over here and the nuclear fallout from nuclear detonations, it's right here in all this very small area. Actually, medical diagnostics adds quite a bit to the average American dose. But you see, this is the lower end of natural background radiation, and then you see a few places mentioned here as to, you know, and there's again Ramsar with that number of 700, which is probably closer to 250, but even 250 is 5 times as high as the highest end of this scale. That's the natural background variability. And then again, look at the red number. The EPA, the NRC, for various, whether it's a public or whether it's for radiation workers, 1 the exact numbers don't really matter that much, and you can dig deeper into those if you want on your own time. But it shows very clearly we are regulating here at the lowest end, below the lower end of natural background radiation. And the question is, does that make any sense? Especially, can we justify the expense of doing that? So on the right-hand side, let me just add, this is the conventional radiation symbol that every one of us is familiar with. Of course, as I mentioned in the beginning, everything and everybody is radioactive. So that symbol already was fairly senseless. It's almost meaningless because everything is radioactive. And no regulator can tell you what is below regulatory concern. That is, what has little enough radioactivity that you don't really need to post that symbol. But what's even worse is the new symbol. This has been internationally accepted for the last few years. And basically it says, if anything is radioactive anywhere nearby, start running. Well, start running from yourself. How stupid can you get? So, but this illustrates the irrationality of our radiation protection regime. So now let's go to radioactive waste. And when radioactive waste is usually considered the Achilles heel of anything nuclear and radioactive. So this is an old cartoon, of course, Dick Cheney up there illustrated. And then, of course, the follow-on is this. Okay. So, nuclear waste is this big problem that we have. It's a sleeping dragon that, we tickle at our peril, and then it awakens and, it will threaten our livelihood and everything else. Well, let's talk a little bit about what we do with radioactive waste. In Germany, my native country that I escaped from 40 plus years ago, actually I immigrated quite peacefully, has a place, you may have seen the press reports, called the Asse, which is an old salt mine. They are right in the center of Germany, where they have put some low to intermediate level waste for the last 40 or so years, and they stopped that about 15 years ago. Well, this is what the Asse looks like. It is a salt dome. There's the surface right here, and then you have layers of salt, and they were folded upward, and then you see here in red, these are the actual underground chambers from the former salt mine. There are others, but the red ones are the one they put that radioactive waste in there. Now, there is a little problem with the Asse, and that is there is some groundwater that is some water is seeping into the old mined-out tunnels. And therefore, the Germans are right now considering, do we have to recover all this waste, take it out of there, because, oh my God, if this mine, gets filled with water, then what happens is going to be an environmental disaster of Chernobyl proportions or of Armageddon proportions, what have you. So a colleague of mine in Germany, his name is right down there, he came up with this graphic because he compared the inventory of radioactive material in the Asse with the radioactivity of the granite that's exposed in the exposed portion of the Matterhorn in Switzerland. And what he came up with was, if he took the Asse and then he added to that another repository in Germany, the Morsleben repository here, the two of them together, that would be about the equivalent of this part of the Matterhorn. And here is the granite, the total height that's visible, and that's about 10 to the 16th becquerel. That's the amount of activity that this granite emits. So let's go to the next slide. This is a little bit more schematic, but what is very clear here is that when we look at the natural radioactivity contained in the overburden, the rock above this salt structure where this waste is, then we come up with basically 10 to the 15th becquerel. That's the largest number, so that basically dwarfs everything else here. And then we look at the activity of all the waste, and that was in 2000 on the same order of magnitude, actually a little less, 3 times 10 to the 15th. That was, well, actually a little bit more, 3 times 10 to the 15th. But then since this waste actually loses its radioactivity with time, in about 100 years or 140 years, it will be actually 2 orders of magnitude less. The key point here is the overburden, the natural radioactivity in the overburden is on the same order of magnitude as the waste inventory in the mine itself. So on the face of it, it looks really stupid to try to remove all this waste in order to remove any hazard. So that takes us back to the good old, United States. Two government agencies are mostly in charge of radioactive and nuclear things, the Nuclear Regulatory Commission and the Department of Energy. And I'm making a very nasty statement here. They are not driven by science, data, or evidence. As a matter of fact, I myself am almost allergic to the term science or scientist. I'm just looking at simple, is there evidence for or against something, or is there not? I don't really need to give it much of a science cloak. So let's go into that. I am not just saying that the DOE and the NRC are dishonest, but these are respected scientists that were involved in nuclear waste projects in the United States, both WIPP, the place where I used to work, and the Yucca Mountain Project. Both of those names most of you have heard. Charles Fairhurst, a professor of rock mechanics at the University of Minnesota. Ruth Weiner, a nuclear waste transportation expert. Warner North, a risk assessment expert. Isaac Winograd, a hydrologist. Eugene Roseboom, both of them with the USGS and now retired, a geochemist. And Wendell Ward, a geophysicist who was in on one of the early nuclear tests that did not test weapons, but tested civilian applications of nuclear detonations. All of these people, except for Ruth Weiner, are now retired, and they actually attacked the DOE and the NRC and said, let me give you a couple examples here. In a letter to the science advisor to President Obama in 2011, they stated that there's a conspicuous inconsistency between what you profess to advance or advocate and basically between your words and your actions, okay, as far as Yucca Mountain is concerned. And just so that you don't think I picked only that one group, there is the General Accounting Office that looked also at what DOE decided and what NRC decided, and what they said when the DOE decided to give up Yucca Mountain, which was an intended repository for high-level waste. They stated that there are better solutions, but the DOE did not actually quote any technical or safety issues, and they did not really identify those better solutions. So again, discrepancy between words and actions. That brings me now to the project where I worked, and where in the last year we have had significant problems. This is called the Waste Isolation Pilot Plant, for short WIPP. It's in the southeast corner of New Mexico, a little bit to the east of Carlsbad. This is about a 16 square mile area. And that's where some radioactive waste from the nuclear weapons research and production sector is being put underground into mined out chambers in salt, essentially similar to a salt mine. And then the salt itself, actually the tunnels creep in around the waste and enclose the waste. It's sort of like a natural trash compactor. This is what it looks like, again, the location right here, but this is what it looks like. There are 4 shafts that go from the surface underground about 2,150 feet, then a room and pillar network, and the waste is disposed of in chambers between these gray pillars. This is the surface here. And for those of you who have been in the neighborhood, these are the Guadalupe Mountains. That's the highest mountain in Texas, Guadalupe Peak right there. That's where I spent the last 23 years of my career. Well, in 1999, we started actually putting waste underground, and for 15 years, everything went hunky-dory. And then early last year, in 2014, a piece of equipment, a salt haul truck, caught fire underground. And you notice the smoke that's going up this particular shaft right here. This in itself was not really a big problem. Such fires occur in mines occasionally. They extinguish them. They spend 2 or 3 days analyzing the cause, try to remedy it, and try to prevent it in the future. And within a few days, they're back in production in a commercial salt mine. In a government project that deals with nuclear things, it's a big production. But what's worse is, since we put radioactive waste underground, we had some systems in place that were intended to mitigate a radioactive release. This was not a radioactive release, this was a simple fire. But the people at the plant were actually then implementing one of those nuclear mitigation measures to deal with a non-nuclear event, and that made things worse. In other words, they changed the ventilation around. At WIPP, we can actually go from unfiltered ventilation, letting running air through the underground, to running that through filters, HEPA filters, and they changed to filtration. Didn't do anything to mitigate the fire, it actually made things worse. And when the underground workers said, you are screwing around with the ventilation right now, and that gives us problems because smoke is going into areas where we don't expect it, so change it back to where you were, they refused that request. There was an accident report written about a few months later, and the accident report omitted that essential fact. So you cannot trust government reports written after accidents to be complete. I brought this up to the attention of the DOE. I actually had to bug them about 4 different times to finally get confirmation that this had happened. And then I asked, are you going to revise a report to incorporate this? You know, government reports, if any one of you has worked in the government sector, you know, there's a Rev 1, there's a Rev 1.1 or the Rev 2, you know, they're revising documents all the time. They refused to revise the report. So that was one problem. The second problem happened about 10 days later. That's when we had a radioactive materials release. Los Alamos National Lab, which sent us some of their waste, they had put chemically incompatible materials into one of those drums, nitrates in combination with organic absorbent, kitty litter called in the press. And that led to an exothermic reaction. You see that up there on the right-hand side, a drum there sort of puffed open because it got hot inside and radioactive materials got released and floated through parts of the underground and contaminated it. And actually some workers got a little bit of exposure, but nothing too significant. On the surface, due to the filtration that kicked in right away, we got very little contamination. You can see the plume right here, and this is a model, okay? These are not actual measurements, but they correspond pretty well to reality. So very little there, 10 milligram is peanuts. Underground, what happened was the event, the radioactive materials release took place over here, and areas that went downwind from here towards the exhaust shaft were contaminated. So there are various areas contaminated to various degrees. And you see the color code up here. Surveyed below regulatory limits, contaminated under 100 dpm, under 2000 dpm, and over 2000 dpm per 100 square centimeter alpha. Now, anyone in this room knows what dpm means? It means disintegrations per minute. I had a unit earlier, it was called becquerel. Becquerel is disintegrations per second. This is a this is a unit to measure contamination. Now obviously, if I use disintegrations per minute rather than disintegrations per second, then I have a number that's 60 times higher than the standard unit, the becquerel, the disintegrations per second. This is very similar to what we see in the press after an oil spill. Normally, when we talk about crude oil and crude oil production, we're talking about production in barrels. What happens when you have an oil spill, whether off Santa Barbara or in the Gulf Coast somewhere? All of a sudden, they're talking about gallons. Same thing happening here. This is intellectually dishonest. And when I asked the DOE about that several times, they said, well, that's the way our procedures are written, and that's the way our DOE orders are written. And when you ask, why are you using these units that make everything look 60 times as bad as it should be looking, somebody else made that decision years ago. So you have to be very careful when you look at doing those events at actually what is being published and what is being released to the public. You need to look at the units. And you need to look at whether people are actually committing shenanigans with those units. It's sort of like going into the store and buying a half gallon of ice cream, and all of a sudden it's only 1.5 quarts, okay? Oh, by the way, when I asked what is below regulatory limits, they didn't put a number to that one. And I had to ask about 3 times until I got the answer for that one. That's 20 dpm. 20 dpm, that's about 1 millirem in actuality. Now, the annual exposure to the average American from natural background sources is roughly 360 millirem. But the average exposure from all sources, natural plus medical, etc., is roughly 600 to 620 millirem. So the dose right there, the below concern, is roughly 1 millirem. That leads me to conclude that most likely none of this stuff is actually going to hurt a fly if people would go in there even without protective clothing and other protective measures. However, that has been done ever since this incident. It happened 1 year ago, and WIPP has still not started receiving waste again. That means it's still shut down for all practical purposes for recovery efforts. Now, every time that a government agency has a problem with something radioactive or something non-radioactive, when they address it then to the public, they always tell you this mantra, well, safety is number one, and everything we do is run under that principle, safety number one. Well, let's see if that's true. February 14 last year, that's where the radiological release was. We didn't know what the cause was. It took several months to figure that out. But originally it was thought that it was some sort of roof failure. That means in the chamber where that drum was, something had fallen down from the top, cracked the drum, and released it. Most of us thought that was highly unrealistic because that area had been freshly mined and it was very stable, so that was the least likely cause for this. Then the local DOE office, Carlsbad field office, issued a press release only about a month later and said, well, now that we cannot ship waste to WIPP from Los Alamos, we're going to ship it to an interim storage site in Texas, only about 50, 70 miles away from WIPP, where they could put it into interim storage. Which means that basically that waste then had to be shipped from Los Alamos to that interim storage site first, and then as soon as WIPP is open again for business, it would have to be shipped from there to WIPP. So it would have to be handled and shipped twice instead of once. So the shipments commenced April 1 through May for 1 month. And then at the end of April, the first accident investigation report came out on the radiological release, and they still didn't know what had caused it, but they were now suspecting that maybe it was something else, but the biggest suspect was still the geotechnical one. That is, something in the roof fell down and cracked the drum. But by May 1, they finally said, well, maybe something chemical happened in one of the drums, because they couldn't find any evidence for something having fallen on the drum. And in May 27 then, they finally said, well, the waste that we have shipped so far to the interim site, we are now going to ask the people who have it stored to take mitigative measures to put it into larger containers, just in case there are drums in there from the same waste stream that might actually experience the same kind of release. What is the point here? The point is that whenever some radioactive or nuclear mishap happens, everyone assures us that safety is number one, and we are going to do everything under that consideration. What is really meant is nuclear safety is number one, and all other aspects are not being considered. Because right here, nobody did a comparative safety analysis or comparative risk analysis, and all safety and all risk is comparative. Everything we do has some degree of risk, so there's nothing with no risk. The shipping from Los Alamos to the interim site and then sometime in the future to WIPP, if they had analyzed the risk of just a simple traffic accident, my best guess is that would have been higher than any kind of radioactive risk that they were avoiding. So when somebody tells us safety first, we always have to ask, have you looked at basically all aspects of your safety? Because if you just say nuclear trumps everything else, you may be overlooking something. And that's what they did right here in this case. I am very sure that if they had to do it over again, they would not ship the waste to an interim site in the meantime, because they had no idea yet about the reason for the original release. Something that they didn't even know about could have happened during this transport. They didn't know, but they just shipped it somewhere else without knowing. Again, that's the simple chance of an industrial or of a traffic accident due to the multiple handling were not considered. So when officials talk about risk analysis, it's always very important to look into, have you looked at all the risks, and have you looked in a panoramic view, or have you just only stared ahead with blinders on? This is actually the contamination or the radiological release at the surface. That means as soon as the release happened underground, there were radiation detectors in the airflow between the event where it happened and the shafts, and they actually found there was radiation, and they kicked into filtration mode, the HEPA filters up at the surface. So the first was 46,000 becquerel per sample. That was before the filters, and then you see the filters worked very nicely. It went from 46,000 to 213,000. And by the way, here we have the standard unit, the becquerel, the disintegrations per second. And then a little bit further away, 1.30, you see the story. The further you go away from it, it declined very rapidly. And then also in time, from the 15th of February through then at April, it declined very rapidly. That's the most dramatic right here. So that shows right away the filtration works. Now, one thing to keep in mind is 46,000 becquerel looks very big. And it's an alpha emitter, so you don't want to inhale this stuff. Nevertheless, each one of us is actually a radioactive source of roughly 8,000 becquerel. So we need to put that into context. Now, if I stand next to you, I'm not going to breathe in any radioactive particles from your body, okay? Because they're confined to your body. So it's a little bit different. I'm comparing a little bit apples and oranges, but still the order of magnitude is, 8,000 becquerel, that's me, and that's 46,000. 46,000 otherwise looks humongous. It's not really. And by the way, this measurement was done by an independent group at New Mexico State University. And here it puts things into context. Again, by the agency of the associated with the New Mexico State University. The average dose from all inhaled radionuclides about 2.3 millisievert per year. That is for the American citizen, and then that's equal to 230 millirem. And the estimated dose, that's a near-field sampling station. That was one that was a little bit away from the release from the shaft. 2.2% of the annual dose. So on the surface, nobody got hurt or harmed, or nobody's going to die probably even one day early because of a cancer he gets because of this. But what we don't have any information really, or the public is not given any information on what is the contamination underground. The DOE has instituted a program now to recover from this accident, from this radiological release, that the first estimates all say will cost $500 million, including a new shaft. And my question was always, okay, you're going to spend now $500 million, including sinking a new shaft. Then please tell me, what is your analysis of how many cancers are you avoiding with that, and how many deaths are you avoiding, or how many lifetimes are you lengthening or shortening by spending this money? They don't give me any number. Basically, the official attitude is, because we are bound by our own orders and regulations, we don't really have to justify anything except give you the regulations. And you just saw earlier in those diagrams what the regulations do. They regulate at tiny percentage of the overall bandwidth of natural background radiation. So the point is, $500 million today, if the DOE says today they're planning to spend that, by the time they actually spend it, it's going to be at least 4 or 5 times that much. And that's your and my money, and it's going to be spent for what? How many lives is it going to save? How many cancers is it going to avoid? If you cannot answer those questions, then it's basically money thrown out the window. So, in response to the question here, do you have a map of the underground that tells me how strongly is it contaminated and what are your decontamination measures? How far are they getting it down now? There's, oh yeah, we are working on it and this and that and the other. But that's a map that they then came up with. Well, when I'm asking for a map that shows me contamination, I'm looking for something like a contour map of a plume that shows me, okay, here's a high area, there's a low area, not just areas like this. This is a really cheap excuse for a map. And meanwhile, the contamination effort is in full swing. They're washing down every wall underground with water. You see the numbers there, 2 gallons per foot down each drift. And then they state to the public, we achieved 95% mitigation in the first pass. So I asked them, okay, what did you start with and what did you end up with? They don't issue the numbers. So take it on faith. Taxpayer, take it on faith. Just give us the money and let us do it. So in the meantime, until this is decontaminated, it's a high contaminated area, so once with over 2,000 dpm, they're entering in these anti-contamination suit. And I challenge you to find out, there are 2 pictures in there of WIPP people that go underground, and the others are from Ebola people. What's the risk from Ebola versus the risk from this kind of radiation? And I think you can all answer that for yourself. But this is where our tax money is being spent. And as a taxpayer, that really irks me. So, I just stole this obviously from somewhere, but there are these various potential ranges of cleanup. We can clean up to a very high standard so that it doesn't exceed 15 millirem per year, or we can go to something with 5 rem per year or 5,000 millirem per year. And you see the EPA and the NRC, they have all these various standards. So depending on wherever I go, wherever I set my goal for the cleanup, it will tell me then, give me an idea about the cost of this. The higher I go on this chart, the more I have to spend. Okay. Or here I have, for example, an analysis that was published by the Government Accounting Office some years ago. You know, they actually came up with some estimates. If I clean up the Nevada test site to 100 millirem, then I spend that much money. To 25 millirem, I have to spend a whole pile more money, and so on and so forth. So it matters quite a bit to what is clean? How clean is clean? That was in the title of Willie Soon's program title, okay? So how clean is clean? That's a very important question, and it's a very important answer that as taxpayers and as technical and scientific people we always should ask. And in a more graphic form, here you see how important that question is, how clean is clean? If we clean up to a 15 millirem standard, then we are talking about, this is for the whole DOE sector, for all the sites all around the country that are contaminated to some degree. If we clean them up to 15 millirem, then we're going to have a cost of roughly $350 million. If we clean them up to much lower standards over here, then we could save quite a bunch of money. And since this chart was actually put together in 2006, the costs have increased probably by one order of magnitude. So it's very significant. And then it's very significant to put that into context. 15 millirem. Why do we clean up to 15 millirem if the average American is exposed from natural background to 360 millirem? And if you include medical procedures, it's 620. Why do we clean up to this? And that's the same curve from a different report. Again, you see the scheme. We heard this morning Ed Calabrese's talk about the linear no threshold theory. As long as WIPP was operating in this according to the start clean, stay clean model, that means we had no contamination. We didn't really have to worry about these concepts of linear no threshold theory. It was a theory, it was something theoretical, but it didn't affect us practically. Now, the linear no threshold theory, LNT, and ALARA, the principle to keep additional exposure as low as reasonably achievable, which actually is a lie. Actually, it should be called ALAURA, as low as unreasonably achievable, because that is the way it's implemented. It's basically, if you can measure it, you avoid it. And since we can measure now basically individual atoms, you know, it becomes completely unrealistic. So now WIPP and every other repository in the future is being threatened by the precedent that we are setting with this potential humongous cleanup effort at WIPP. And these are some quotes. The general manager of the management operating contractor at WIPP. That's what he verbatim told me. If I can avoid 1 additional millirem, I will. Radon is the largest cause of lung cancer. Both of those statements are patently false. Okay? There is no evidence. I'm not even saying they're unscientific. There is no evidence to support either of these statements. Okay? Again, 1 millirem, 360 we get each year. That's from natural causes, the average American. But since he has an unlimited budget and everything runs under LNT and ALARA principle, he doesn't need to justify it. And I just attended the American Nuclear Society meeting in San Antonio early in June, and that's what I heard informally from colleagues over there. So a lot of people know by now what Ed Calabrese told us this morning. LNT is based on a total fraud, and the ALARA is just a public relations ploy just to sort of put people at ease that don't really know anything about nuclear and radioactive processes. So what I'm advocating is, again, I didn't invent this. Bruno Combi, a French environmentalist who was converted to become pro-nuclear, put that into his book. He said, because we have the total absence of negative effects of low doses of radiation, the ALARA principle should be replaced by a principle called ALAN, as low as in nature. And as you saw earlier in the picture on Ramsar, the upper end of the natural range is actually not 100 millisievert a year, but 250 millisievert a year. So that's where I disagree with him. We should set it at 250. Now, a little insert right here. Right now, before the NRC is a petition by 3 different petitioners, but one of them is called Scientists for Accurate Radiation Information. And a couple of people in this room are signers of that petition. Dr. Orient is one of them. Ed Calabrese is one, and a few other people. And I just submitted my own comments to support that as well. So you have a chance right now to actually submit comments until early September to the Nuclear Regulatory Commission. That is the first time in the history of the NRC that this has been actually put in a formal, has been started as a formal process to actually get rid of LNT and ALARA, to force the NRC to actually justify whether or not they'll continue basing their regulation on that. And the DOE and the EPA eventually all sort of follow the NRC's lead. So this is very important. If you have any association with nuclear and radioactive matters, and you have misgivings about LNT and ALARA, this is the time, this is the place to do it. So look it up on the web. And I can give you later on, after the presentation, the docket number. I just thought I would throw that in for fun. This was the German Pope of radiation protection a few decades ago, and he gave this statement, and I found this cartoon in the internet, and that's really true. You know. And this is my motto. I add it to every email that I send out, because I'm really bothered, and you should be too, by people who are insisting on compliance with regulations, but they never justify the basis for those regulations. And they cannot defend those regulations, except saying, oh, that's what that authority says that. I mean, what was the motto in the 1960s and the 1970s? Question authority? Why has that disappeared from our vocabulary? DOE conceals and ignores relevant information. Let me give you a few quick examples. The intriguing thing is now we have contaminated areas underground at WIPP. Again, salt mine half a mile below the surface. The natural background down at WIPP is much less than the one on the surface. Because first of all, we're shielded against cosmic radiation by all the overburden above us, all the rocks that's above us to 2,150 feet. The second part of it is that salt, the medium that we're in, the rocks that we are in, is probably it's definitely one of the least radioactive rocks around. It's much less radioactive than the average crustal rock because it contains no uranium, no thorium, and no potassium, the main radionuclides in nature. So that the radiation levels underground at WIPP are less than 20%, and actually I have a source that says 7% of what's up on the surface. So the big question actually to ask is, now that it's contaminated, are we anywhere close to what we have on the surface anyway to begin with? The DOE still doesn't answer that question. One word of praise for one branch of the DOE right here. The DOE has a branch called the Office of Science, and that Office of Science has a low-dose research program, and the low-dose research program publishes this chart, and you can find it on their website, where they have scales from 0 to 1 millisievert, 0 to 10, 0 to 100 millisievert, and so on and so forth. So the scales get bigger as you go up. And right here, it shows natural background US average, 3 millisievert or 3.6 millisievert per year. It also shows a natural background in Ramsar, which goes in the range up to 250 millisievert. And it shows also where all the regulations are. So there's one branch of DOE that actually knows reality. And one very audacious lady who used to run that and may still run it, I'm not quite sure whether she's still in charge there, who actually put this chart together and ran it through the bureaucracy and got it on the website. And I've been holding up that chart in town hall meetings to my local DOE people every time and said, show me on that chart where you are. And then they came back with this here, the highest air sample right here. And this one was the high dose when they changed the, that was the highest dose received, 7.92 millirem, and this one here was something that they swiped off a filter. And you see here, again, we're in the area way below natural background. Nevertheless, they want to spend $500 million to remedy that. So, since I had so much fun dragging this, kicking and screaming out of the DOE, I was thinking of this sort of new poster boy for the DOE information practice. You know, I had to basically drag it out of their cold dead hands because they were not voluntarily releasing much. One other point to put this all in context, 1961, we had only 8 miles away from WIPP, we had an underground nuclear test, Project Gnome, part of the Plowshare series, investigation into civilian applications of nuclear detonations. This was the resulting cavity, and actually the first re-entry into that cavity happened only 6 months after the shot. We now have had almost 1.5 years since the radiological release at WIPP, and yeah, we have had people down there, but we're not back to operations yet. And just to sort of give you a better idea of what happens there, was that radioactively laced steam actually raced up the shaft and escaped and vented out. And nobody, the DOE actually owns this site too. And they have not said how much bigger or smaller the the WIPP release has been. You need to put things into context. Nobody got hurt as a result of that. No people have died early deaths or gotten cancer as a result of that. So you need to do comparative risk analysis, or you need to understand what is the risk compared to other stuff we have been exposed to in the past. And here we have really a worst case example. Okay, last point, DOE wastes time and people. When we hear about, when we hear about the risk of anything dangerous, one of the principles invoked is always the precautionary principle. Well, just in case, stay on the safe side, etc. Well, we have no indication that radiation in the low-dose area, especially in the LNT, especially in the hormetic area that we heard about this morning, does any harm. It may actually do some good. However, we're behaving in such a way that we say, well, we don't really know that it does harm, we assume that it does harm, and we're going to mitigate it. So we're spending $500 million or $5 billion or whatever. We are not really behaving much better than those guys in the Middle Age. They had no evidence that witches existed, they had no evidence that witchcraft existed, but they applied the precautionary principle. Just in case they do exist, let's make sure and burn a few of them just to be on the safe side. And this lady actually has a name down there. And I took this idea actually from an article that I really heartily recommend to anybody. William Clark, Witches, Floods, and Wonder Drugs. There were these risk assessment experts during the Renaissance, and they made a science out of finding witches and identifying witchcraft. And they assessed the risk, and then they used the precautionary principle. And they were trying to create a witch-free world. And as an ex-German, let me put something really nasty in here. More witches were burned in Germany than in any other country around the world, in Europe, when the witch craze was going on. So from 1450 roughly to 1750, that was sort of the period when they burned witches. It was not during the Middle Ages, it was after the Middle Ages, not during the Dark Ages, after the Dark Ages, you know, when they had risk assessment experts. The effort was to get Germany, I use the German term, hexenrein, pure of witches. We all know what happened between 1933 and 1945 in Germany. The effort was to make Germany judenrein, pure of Jews. Now, since roughly 1998, Germany's on the train, jumped onto the train, actually is leading the train, driving the train to get out of nuclear. So now the effort for the last 16 years in Germany has been to make Germany strahlungsrein, radiation pure, radiation free. Wouldn't it be nice if the Germans stuck to, in regards to purity of something, to beer? And just to bring that home a little bit more, on the Cologne Cathedral there are these two stone figures. One is Katharina Hinault. She was a postmaster. She was burned as a witch at the stake in Cologne. She was, her name was given to the authorities at the time, probably by some competitors that wanted to get her out of the way and accused her of being a witch. And this one here is Friedrich von Spee. He was a Jesuit who actually wrote in 1631 the Cautio Criminalis, which was the first book that fundamentally attacked the witch hunting craze. And that was the beginning of the end of the witch hunting craze. It took almost another 100 years to actually get completely rid of it. What we need more people who speak up, and we don't actually risk being burned at the stake. So I ended with this picture, and I stole this shamelessly from Jay Lear, who in 2000, at the 20th meeting here in Colorado Springs of this organization, advocated for a society for the humane abolition of regulations that kill. I put the picture in there, I stole it from the internet, and that's what we really need as far as radiation regulations are concerned, that not only can kill repositories, but can kill people if we let the bureaucrats do it. So please do what you can, especially with a petition right now before the NRC. Thank you for your attention.
When you mine uranium, you're dealing with a radioactive substance. So you take a whole bunch of ore and you concentrate it. You make the uranium fuel rods for a nuclear plant. You use some of it, and then you have radioactive waste. Mm-hmm. Somebody proposed the idea that you take that radioactive waste, which is now less radioactive, correct, mix it with the old mine tailings, which aren't, and put it back in a mine, and you've solved your problem. In fact, you've created something that's less radioactive than when it was in the ground in the first place.
Well, in response to that, is it still on? Yeah. You very clearly said that depleted uranium is less radioactive than natural uranium, and of course uranium has a half-life of 4.5 billion years. That means the activity is very low. It emits a little bit of radon and radon daughters. So all the excitement and hullabaloo about depleted uranium has much ado about nothing. Okay? It doesn't, and by the way, depleted uranium can be re-enriched, actually. You can still get more U-235 out of it, and it can be used as feed material for a breeder if we ever get there. Dr. Robinson can probably tell you more about that than I can, but am I correct with that? Yeah, thank you.
You know, now that we have a friendly Senate, I don't see any action, and Monsieur Harry Reid has been removed, right. Who I believe was the primary stopping point for using Yucca Mountain. Right. Has there been any activity politically by the yes. Senate or whoever can do something about this to finally consolidate the waste material at Yucca, the high-level stuff I'm talking about?
There are some efforts in the House. They're probably not going anywhere because they don't have a veto-proof majority in the Senate. But let me add maybe a more fundamental point to that. We are always accusing politicians and journalists of basically feeding us misinformation on nuclear and radioactive things. We collectively, scientists and engineers, not any one of us individually, but we collectively as a class of scientists and engineers, we caused the problem. And the journalists and the politicians are following our lead that we established during the past 50 years. We have hyped, and especially, of course, the radiation protection and radiation control establishment, because basically they would be left without jobs, most of them, if this radiophobia actually were finally cleared out. While I blame Harry Reid and his feckless political colleagues, the problem didn't start with him. He's just using something that we handed him on a silver platter. Yes.
As a non-scientist, I'd like to ask a naive and somewhat flight of fancy question. Why can't we take the nuclear waste and entomb it and embed it in the bedrock of the tectonic plate at the point of subduction, so that in a kind of terrestrial scale down escalator conveyor belt, it gets pulled down hundreds of miles until it finally gets melted in the molten center of the Earth and out of sight, out of mind.
That's a concept that has been considered, but it is unnecessary. Again, everything on planet Earth is radioactive. So and then when you put it into a plate boundary like that, you actually have less control over that than if you put it into a salt mine in an old cratonic area, which means an old, really old shield area, it's called, in the middle of one of those plates, where we know, based on geological evidence, that nothing has happened there geologically for hundreds of millions of years. And that's such an area where we have WIPP, not necessarily in Nevada, but it's whenever people talk about radioactive waste, they often have the assumption that we can put this stuff only where it is the safest place to put it. No, we don't. We need to put it into a place that is safe enough. Because if you put it into the safest place, then you're on that search for the Holy Grail that would last forever. Okay? So something safe enough. And to put it into an old salt mine, for example, or into a freshly mined salt mine, specifically excavated for that purpose at WIPP, for example, that's safe enough. The salt at WIPP has been there for 230 plus million years. The half-life of plutonium is about 25,000 years. After 10 half-lives, any radioactive substance basically has decayed to background. So 10 half-lives would be 250,000 years. 250,000 years versus 250 million years that this area has been tectonically stable. So no, never mind. For a geologist, there's no nothing. It's not going anywhere. And by the way, the concentrations are so low. And by the way, Bernie Cohen made the argument in the last article in the books that you can look at out there that if you bury it anywhere, just 500 meters deep, even if you don't bury it in salt, just average crust of rock, the average velocities of water or formation fluid, that deep it's not fresh water or drinkable water anymore, formation fluid, I call it therefore, are so low that even if it comes back, it will come back in concentrations that are no never mind. Again, that will not exceed background radiation, at least not the highest range of background radiation that we have planet-wide. So it's not necessary. If you want to, you know, if you're a billionaire and you want to blow your, whatever, $50 billion on such a project, by all means, be my guest, but I don't think anyone can justify using taxpayer money for that. It's safe enough is good enough. Mm-hmm.
A few years ago, there was a disaster in Fukushima, Japan. Can you comment on the levels of radiation that were experienced by, some people must have gotten a lot, some people maybe a little bit. What were the levels, and were there any deaths? Were there any adverse effects in anyone? Are there any studies going on regarding that?
Thanks for the question, because it really gives me a chance to really address a real risk. Fukushima, the earthquake and the tsunami killed 25 to 30,000 people. Nuclear radioactive things killed nobody, harmed nobody, didn't make a mosquito sneeze, okay? And the concentrations were far below what you have in Ramsar, all right? And just to put maybe a little bit of a dollop of ice cream on top of that argument, let's look at Chernobyl. Chernobyl was a bad thing that happened, and it was mostly caused because the Russians built the reactor without confinement, and they did some stupid things. But let's look at the consequences. Chernobyl killed between 30 and 50 people. That's it. I'm sorry for sounding sort of crass, but a garden variety plane crash kills more people than Chernobyl. And most people who died as a result of Chernobyl, most people who died as a result of Chernobyl, and all people who died, most people who died as a result of Chernobyl, and all people who died as a result of Fukushima died because of radiophobia, because of ignorance, because of fear instilled by regulators, including at the time our NRC that recommended evacuations of areas much larger than the Japanese had even thought about, told Americans to stay further away from Fukushima than Japanese told their people to stay away. Nobody will die, and probably, and most likely nobody will be detected as having gotten cancer or died a few days earlier as a result of Fukushima. I myself went to Chernobyl a year ago, and I had a dosimeter with me, and on the flight from Houston to Amsterdam, I got about 5 to 6 times the dose over 7 hours than what I got spending 7 hours in the restricted area in Chernobyl, just to give you an idea. Yes, ma'am.
It's turned into 2 questions, but I'll be really, really fast. The fear factor is the worst thing. I mean, I'm still reading. People are still looking me in the face and saying, we've polluted the entire Pacific Ocean from Fukushima. I mean, they say that. They believe that. They believe that there are things being found along the West Coast. I mean, that's just sick, and I don't know how you can deal with that kind of fear, the fear thing that people just keep escalating. Okay, but the other question is, almost 45 years ago, one of my daughters, maybe it was 35 years ago, in high school wrote a report on breeder reactors, that's what the title of the paper was. And of course, all the other nations that have nuclear plants have processing plants to recycle the waste uranium. I mean, the waste from our nuclear plants. Why and when are we ever going to do anything like that in the United States? We keep worrying about Yucca Mountain, keep worrying about these other places when we know what to do with the spent fuel. You fix it so you can re-spend it. And so, I mean, I'm still eternally puzzled by that. Nuclear is so safe, so clean. Nobody's hardly ever died from it.
Right.
Nuclear power, I mean.
Yeah.
Yeah.
The word spent fuel is a bad word. It should be called used fuel, and actually most people are saying used fuel. Most people in the industry are now calling it used fuel because it's not spent. There's still a lot of energy in there. There are today, there is UK, France, Russia, and Japan, I believe. Those are the countries that do reprocessing. Reprocessing was killed for political reasons in the Carter administration in the United States, and it should be revived again, yeah. Yes, sir.
There's an investigatory principle expressed in Latin, cui bono in English,
Yes.
who benefits?
Yeah.
And we've seen in your talk and elsewhere lots of evidence of economically disabling radiophobia.
Yes.
So do you have an opinion as to who benefits or who might be benefiting, or is anyone benefiting from the West's rational obsession with minute hazards from radiation?
Okay, that could get me on the soapbox for an hour. I'll try to make it short. Actually, everybody benefits except the taxpayer, okay? What we have is, we have the Department of Energy that benefits from making things complicated because they can build an empire. Part of the DOE are the national labs that usually try to usually tout their independence. We have 2 national labs participating in the WIPP project, Sandia and Los Alamos. And neither one of them, neither one of their employees involved with WIPP ever opens their mouth about the idiocy of current radiation regulations. So their independence is nonsense. And of course, the bigger the problem, the more work and research for the national labs. Then you have the anti-nuclear people, of course, and the more they talk up the thing, the more, you know, exposure, pun intended, they get, and the more fame and glory. And then you have, and I'm saying that deliberately, then you have the local leaders. We have them in Carlsbad. And they are interested in bringing as much federal money into the community as they possibly can, and they don't really care whether it makes sense or not, as long as it's being spent there. So you have an iron triangle or quadrangle. Everyone interested in getting the money and spending the money. And the average taxpayer is getting the shaft. That's the way it is. Then you have, of course, the radiation control community. They're not interested in changing things because they're, you know, making a good living off that. I have had colleagues accost me in the hallways of professional conferences and say, "What are you saying? You're you know, taking away my job and the jobs for my children and grandchildren." Yes, maybe so you can do something more useful. Hopefully. Yes, sir.
You say the human body is radioactive, and I assume that's due to potassium. So what % potassium is in the human body?
I think I would have to look it up, but I believe potassium is potassium 40 is the biggest contributor to the becquerel in the human body. You can look that up on websites. I have it somewhere in the sort of extra slides on the end of my presentation. I'll be glad to give you a copy of it. I just don't have it in that
a few percent,
hard drive up here. Pardon?
It's just a few percent
potassium 40 is a very low percentage of overall potassium, but it is a beta and slight gamma emitter, and it contributes actually, I believe, most of the activity in the body.
Oh, okay.
But I can give you more stuff, you know, offline on that.
Yeah, the potassium in your body would cause the radiation detectors in the small parts, measuring devices at the power plants to go off by a factor of about 10.
Yeah.
So if I could cut you up in little pieces, put you in, it's called a SAM, small activity monitor, you wouldn't pass. We couldn't get you out of the power plant.
Right.
And the other issue, I was at Fukushima a week after the event, and the parking lot at the hotel read about 400 microart per hour, 20 times or so what our natural background would be here, but not as high as some places on the planet.
Exactly, yeah. Okay, thank you.